Previously, we trained our Linnet model in the SciFire dataset. As the model accuracy fell quite short, there were also signs of overfitting. While our model was not very well trained, it was still able to generally predict a majority of the validation images. As mentioned earlier, however, the SciFire dataset is going to be more difficult to classify due to the added depth, variety, and inherent complexity of the training images. For this reason, our very same Linnet model that performed very well with the MNIST dataset is now having issues classifying our SciFire dataset accurately. Let us now discuss how we can fine-tune our network to provide a better performance. Two main issues that we're currently dealing with are the accuracy not being high enough, converging to about 63%, and the network seems to be overfitting our training data. The first issue can be tackled using a variety of modifications to our Linnet model code, keeping in mind that the modifications we apply in this tutorial are very case-dependent, and fine-tuning your model capacity is often a very specific process that is unique for each specific deep learning task. However, fine-tuning your model is important and can oftentimes improve your model's performance significantly. Therefore, it is essential that you always try and modify your model to see just how these modifications improve the effectiveness of your model. When it comes to improving accuracy, I have had good experience with the following three modifications. The first modification will be focused around the learning rates. As previously discussed, the Atom Optimizer computes individual adaptive learning rates. However, it is still important to specify a fitting learning rate for optimal performance. A learning rate that is too high can often lead to lower accuracy. However, a lowered learning rate can help a neural network learn more effectively when a more complex dataset is involved. At the same time, a learning rate that is too small can significantly slow down your training performance. In our case, through both analytical and empirical observation, one can conclude that the training process is quite slow, as the training and validation accuracies are not significantly improved from one epoch to the next. For this case, we will increase our learning rate from 0.0001 to simply 1 times 10 to the negative 3. And running this cell will solidify our changes to our model. Let's make sure to instantiate a new model and rerun our training process. We will move forward to train our modified model and then reevaluate its performance. I will see you guys in a bit. Welcome back. Clearly adjusting the learning rate was a positive modification to our model, as our validation accuracy goes up by roughly 7%, and the training accuracy increases as well. Overall, we see a faster increase in accuracy as the training process continues. Yet, our overfitting issue still persists, which can be visualized by looking at the graphs. The error is definitely smaller, yet overfitting is quite significant. Although the improvement in accuracy was also quite reasonable, it still does not meet our standards as to how high it should be. However, it was useful to see just how a small modification to our model can affect our accuracy. Another modification that is effective is simply adding more convolutional layers. This can help our network extract features more effectively and can also lead to improved accuracy. So let's simply add one more layer to our network. In doing so, a relatively common architecture in defining convolutional layers is one where each layer doubles the depth of the output of the preceding layer. The initial depth, the depth of the input image, is 3, and we will specify a depth for conv1 corresponding to 16 output channels, which is then going to be doubled to 32, 16 to 32, and then 64. Since, as you may have already noticed throughout this course, the depth of the output of the convolutional layer has consistently increased as you proceeded from one convolutional layer to the next, as we internally increase the number of filters to extract highly sophisticated information pertaining to the forwarded input. We use convolutional layers to make the network much deeper, and the deeper it gets, it extracts more and more complex features. So it would be reasonable to proceed by doubling our depth with the second convolutional layer consisting of 32 output channels and a third convolutional layer, self.conv3. And that's going to take in 32 input channels. doubling that to 64, with a kernel size of 5 by 5. As such, the appropriate vector being fed into our fully connected layer will be 5 by 5. That will not change, but the number of output channels coming out of our last convolutional layer will be 64. And we ensure consistency in our forward method as well, 5 by 5 by 64, and applying the ReLU function to this third convolutional layer. Simply copying and pasting the following, and making sure that this says self.conv3x, and we should be good. The added depth of this convolutional layer will help our network extract features more effectively and lead to improved accuracy. However, going back to our graph, it's worth noting that our model was subject to significant overfitting. In such a case, it would make sense to use a smaller kernel size, as a larger kernel implies more parameters, a higher level of expressive power, at the cost of a higher risk of overfitting. Considering this trade-off, in our specific case, it would make sense to use a kernel size of 3. However, when in doubt, it always helps to simply test different kernels. In our case, I simply found this to yield better results. And also, previously in the MNIST dataset, we did not make use of any padding. Since we are dealing with a more complex dataset, it would make sense to preserve the edge pixels of our image by including padding to ensure maximal feature extraction, with a padding is equal to 1. And we do that for all convolutional layers. Padding equals 1, padding equals 1, padding equals 1. In that case, the final vector that is fed into the fully connected layer is dictated by the image size, which is halved at every max pooling layer. The image starts off as a 32 by 32. After the first max pooling layer, it becomes 16 by 16, the second one 8 by 8, and the third one 4 by 4. So eventually we'll have 4 by 4 by 64, and doing the same thing in the forward method. And having performed the necessary adjustments in fine-tuning our model, let's try training it, and see how this ultimately affects the training process. Having retrained the model, the overfitting issue has indeed persisted. However, notice the validation accuracy has now increased to 71%. This is quite a modest increase from before, but it is a step in the right direction, and we'll look to take care of this overfitting problem once and for all in the next lesson.